Inside this facility, the strongest magnets on Earth begin as nothing more than metal dust. Tons of alloy are melted, crushed, and shaped with microscopic precision, forming the invisible force that powers motors, generators, wind turbines, robotics, medical scanners, and nearly every device we depend on. Every day, millions of industrial magnets are born here, and it all begins with metal, heated, shattered, aligned, and transformed through a process that demands absolute perfection. This is how the world's most powerful magnets are mass-produced. The journey starts with the elements themselves. Neodymium, iron, and boron, the foundation of the modern rare earth magnet, are weighed with exact precision and loaded into vacuum induction furnaces. Inside these sealed steel chambers, the atmosphere is replaced with pure argon to protect the metals from oxygen. The furnace ignites, heating the charge to over 1100 degrees Celsius. Slowly, the metals melt into a shimmering pool of liquid alloy. When the mixture reaches perfect uniformity, the furnace tilts, pouring the molten metal into long molds or onto spinning copper wheels for rapid cooling. This strip casting method forms thin flakes with a finely controlled crystalline structure, critical for achieving maximum magnetic strength later in the process. Workers inspect each batch using X-ray fluorescent scanners, confirming chemical composition down to tiny fractions of a percent. If the alloy deviates even slightly, the finished magnet will fail the strict industrial standards required. The perfect alloy is the blueprint for everything that follows. Once the alloy has cooled, it is far from being a magnet. It is a hard and brittle metal chunk. These ingots are lifted by cranes and fed into massive crushers that break them into gravel-sized pieces. But breaking is not enough. To achieve the magnetic properties needed, the alloy must be reduced to an ultrafine powder. This is done using hydrogen. The alloy pieces are loaded into sealed tanks and exposed to hydrogen gas, which seeps into the material and causes it to fracture naturally, a process known as hydrogen decrepitation. Within hours, the blocks collapse into coarse powder. Next, the material is transferred to a jet mill, where high-velocity airstreams smash particles against each other, reducing them to 3 to 5 micron powder, finer than flour. These particles are stored under argon to avoid oxidation, since even a thin layer of rust would ruin the magnet's performance. At this point, the alloy has transformed into a soft metallic dust, ready to be shaped. powder now approaches its first real transformation. Specialized machines load the dust into precision molds. Around these molds, powerful electromagnetic coils generate a directional field up to 15 kilo-oersted. Under this invisible influence, each microscopic particle rotates and aligns its internal magnetic axis. This alignment, created before the magnet even exists, is what gives it extraordinary strength once magnetized. When alignment is complete, hydraulic presses exert forces of 1 to 3,000 tons on the mold. The powder compacts into a fragile chalk-like block known as a green compact. These blocks hold their shape, but only barely. They have no magnetic power, no durability, and only a fraction of their final density. Still, their internal orientation is perfectly set. The groundwork for high-power magnetism has been laid.
Prisidentublin, Hokwinsin, Lupanbonshin นะครับ ที่ดับลินเซงลิบรองเรื่องเชิญนักกวดสิบศูนย์แจกทุกดิน
The green compacts move along conveyors into the most critical environment in the entire factory, the sintering furnace. Here, temperature control must be exact, down to a few degrees. First, the compacts heat to around 600 degrees Celsius to remove moisture and volatile impurities. Then to 900 degrees for internal grain restructuring. Finally, the temperature climbs past 1050 degrees, where the particles begin to fuse at the molecular level. For hours, the compacts are held under vacuum at this extreme heat. Slowly, they shrink by nearly 20%. Their density increases. Internal grain boundaries form. What emerges is no longer a fragile chalk block. It is a solid, dense magnet core with the strength to survive machining. The sintering process determines coercivity, energy product, and overall performance. A single mistake in temperature or timing could compromise the entire batch. Precision is everything. Even after sintering, the magnets are not complete. To push their magnetic properties to industrial standards, the factory performs heat treatment, each manufacturer using closely guarded temperature profiles. Magnets are placed into ovens and heated between 600 and 900 degrees under controlled atmospheres. This step stabilizes the internal crystal structure, dramatically increasing the magnet's ability to resist demagnetization for high-performance motors or electric vehicles. Additional elements such as dysprosium or terbium may be diffused into the grain boundaries to withstand extreme temperatures. When heat treatment is complete, the magnets have the internal strength required for the world's most demanding applications.
Look at this spike here during the thermal cycling.
It's within the acceptable deviation range, but worth monitoring.
The magnets are now solid, but still rough and oversized. Precision machining begins. Diamond wire saws slice blocks into smaller pieces. Multi-axis CNC machines grind each surface to exact dimensions, often within 0.02 of a millimeter. Coolant flows continuously to prevent heat buildup because sintered magnets are extremely brittle. Any excess vibration, temperature spike, or incorrect feed rate can crack the material instantly. The machines shape cylinders, arcs, wedges, rings, and custom forms used in everything from hard drive motors to surgical tools. Lasers inspect each surface, mapping irregularities in microns. The magnets must meet exact tolerances because even tiny variations impact efficiency inside electric motors and generators. When machining is done, each piece is sharp, precise, and ready for protection. Neodymium magnets are powerful, but they have one weakness: they corrode easily. To protect them, the factory applies multi-layer coatings. Most magnets receive nickel-copper-nickel plating, a hard, bright silver shell that seals the material from oxygen. Others receive epoxy, zinc, gold, or parylene depending on their final use. Before plating, the magnets are degreased, rinsed, and acid-treated. They move through long plating lines where electrical current bonds layers of metal onto the surface. Thickness is measured using eddy current sensors to confirm uniform coverage. A good coating ensures the magnet can survive decades inside motors, exposed to vibration, heat, and moisture. Without it, even the strongest magnet would crumble over time. Up to this point, nothing in the factory is actually magnetic. That changes now. Magnets are loaded into a chamber surrounded by heavy copper coils. A massive electrical pulse, 2 to 4 Tesla, is released in a fraction of a second. The energy is violent and instantaneous, locking the internal domains into permanent alignment. When the pulse ends, the material becomes one of the most powerful permanent magnets humanity can engineer. Workers now handle them carefully. Even a small magnet can pinch skin or snap steel tools out of place. Larger magnets must be separated with spacers because their force can damage equipment if brought too close together. Magnetization is the moment of transformation, where the invisible power finally emerges. Every batch undergoes strict testing. Gauss meters measure surface magnetic field strength. Full force machines test how many kilograms each magnet can lift. 3D coordinate measuring systems check geometry. Some samples go through salt spray chambers for up to 96 hours to test corrosion resistance. Others are scanned for internal cracks using ultrasonic or X-ray inspection. Industrial magnets must meet demanding specifications, and even minor defects can compromise performance. Only the magnets that pass every test move forward. Finally, the magnets are ready for shipment. These are no ordinary products. Strong magnets must be packaged carefully to avoid interfering with vehicles and equipment during transport. Workers use cardboard spacers, steel shielding plates, and magnetic neutralizing layers to keep the fields contained. Boxes are labeled with handling warnings and loaded onto pallets destined for motor factories, wind turbine plants, robotics manufacturers, electronics companies, and more. From metal dust to precision-engineered powerhouses, this is the incredible process behind the magnets that drive the modern world. Quiet, invisible, and essential, yet built with some of the most advanced manufacturing techniques ever developed. This is how millions of industrial magnets are mass-produced every single day.
The journey from micron metal powder to humanity's strongest magnet